Share my screen. So, hello everybody. I'm Dimitris Antorineos from Democritus, and today, together with my colleague Andreas Konomakis, we'll present you later on the third pilot, the third demo. A couple of words about the PALANTIR framework is that it is designed to help small medium enterprises to protect against cyber threats. The goal is to provide SMEs with the necessary tools to protect themselves from cyber attacks. And the three main components of this framework is the identification, protection, and the response. The objectives of this pilot, in contrast with the other two pilots that have taken place, is that it is targeting telco organizations that have complex infrastructures and critical cyber protection requirements. So, as the security expertise is higher than in the generic SMEs, small medium enterprises, the PALANTIR components can be better integrated on premises and be part of the network operator CM solutions. This pilot will demonstrate the capabilities of the PALANTIR to detect the attack, real-time alert, and respond to the attack automatically or manually. Share the threat with other PALANTIR-enabled organizations, and provide attestation of the infrastructure and the running applications. The agenda today will be the first demo, the dashboard and the attestation presentation from our colleagues from UBTech, the crypto mining and threat sharing between telco organizations from Telefonica, and UPM, sorry. And the denial of service attacking in 5G environment which will be demonstrated by Democritus. I would like to remind you, we will also present it in the final demonstration, but there is a questionnaire that we would like to share with you and spend a couple of minutes to complete it. And that's more or less. I will give the floor to UBTech to share the screen.
Okay, good morning. I'll share the screen.
Hello everyone, I'm Dimitra Vangelisi, and I will present dashboard and the station with Natalia Hatsiafi. We have currently performed attestation to portal and catalog. So what is attestation? The attestation is a process that aims to keep both the components and security capabilities unaltered and free from any malicious modifications. First of all, you have to upload the jars of the components to Min.io. Then the admin user will be able to see a list of the unregistered components. After reviewing them and verifying that they're not malicious, you can register the components to attestation. The registered components can also be validated by the admin. Once the components are registered and tested, any modifications to the jar files can lead to mismatch with the original uploaded components, causing the attestation to fail. The attestation process will, for the components will be presenting to the following video.
Okay, so since the video is rolling, maybe we should comment on top of it. Now what we are seeing is that we are actually seeing a dashboard where we have uploaded artifacts. We'll show you in a presentation after this demo how this low-level mechanism is working. Actually, the attestation is multi-level, so it can refer to both the platform and the uploaded capabilities. Now we are seeing a demo towards the capabilities. So practically, what is happening under the hood, and allow me to share my screen just to show you what exactly is happening and how these failures. Okay. 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 There are three distinct mechanisms which are complementary. They work and operate under the same principle, and the principle is that they rely on an integrity measurement of the subject that is going to be attested. So practically, when we are talking about the signaling of the attestation, we are actually referring to the fact that we have golden referent measurements of what we want to attest. The subject of attestation may refer to practically the bootloading process, so the system level booting, and thus referring to system libraries and underlying kernel object. It may refer to the PALANTIR component itself, because PALANTIR can be subject to attack, so it wants an attack surface. And on top of that, the catalog, the SEC artifacts that are uploaded in PALANTIR are also considered to be an attack vector. As such, these multi-level, let's say, multi-layer attack vectors have to be taken under consideration during the golden reference measurement process. That means that we have an offline process according to which we get the signature and the reference values of the elements in order in real time to be able to prove that their consistency is intact. And the flow, abstract flow for all three mechanisms is actually the following. That first we are checking we are booting the TPM server if it is virtualized, or we initialize it if it is in a hardware version. Then we are actually provoking an extraction of the measurement from the system. We compare it to towards our golden reference, and then we check if it is match or match in order to spot specific integrity failure. to this, as you saw in this when we uploaded jar, which was actually rejected by the system, and the fact that it was rejected is that it could not be verified regarding its integrity against a golden measurement that was offline provided. And this was actual demonstration of a runtime configuration integrity verification mechanism. So PALANTIR comes in hand with three mechanisms that actually are exposed in a homogeneous way. At the end of the day, the user is getting just an API called prover/attest, attest integrity of subject A. But under the hood, these three mechanisms are operating with different preconditions and offer different guarantees in the runtime environment. The first, the fundamental, as we call, is the security capability host infrastructure, or abbreviated the SCHI, which is responsible for the verification of the measurements of the underlying host that PALANTIR is installed on. That is to say, to be very practical, that if we install PALANTIR, or if we have components in the bare metal installation, in the bare server, and the server is somehow compromised, that is to say that the underlying operating system or someone that is able to actually change the firmware or something low level happens, then the secure boot process and the integrity measurement architecture based approach of the SCHI mechanism notifies us that a specific binary that takes place in the boot process is considered to be compromised, and as such, the entire underlying infrastructure is compromised. The actual pros and cons is that this mechanism actually attests the boot process. It covers the integrity of the entire platform, even the bit sequence, but it provides immunity to binary manipulation. That means that it relies on the checksums of the binaries that are used prior to their loading in the memory. That means that there are additional types of attacks that can be applied in our attack surface, which include more sophisticated attacks. These attacks actually relate to manipulation, to real-time manipulation of the memory. So practically change the binary after it is loaded in the memory. So we need additional mechanism, which is to provide, as we say here, immunity to memory manipulation. And this is practically provided by the sub-mechanism that we call runtime CIV, runtime configuration integrity verification. And this, according to this sub-mechanism, the extraction of the golden reference measurement is extracted dumped by the memory, and is checked against the golden reference measurement, as my colleagues showed previously in this UI. So practically, what we saw previously is we saw the failure message of the runtime CIV agent stating that this specific jar is unable to be considered trustworthy because it fails during the memory loading process, and as such, we cannot continue the process of relying to this core library for running the PALANTIR. Last but not least, I don't want to cannibalize your time. There is a third mechanism which we consider to be the more experimental one, and it is the more experimental because it may provide the ultimate guarantees in terms of security, because it provides immunity to extremely sophisticated attacks like ROPs, etc., but it relies on a different principle, the principle of generating measurements, hashes, from the control flow of the process itself. And the extraction of this control flow, as we also very thoroughly described in the respective deliverable D4.4, are considered to be computational intensive, and as such, because the graphs that are generated when a process is running in CPU are extremely heavy to be exhaustively calculated, the mechanism itself is not always deterministic, as we say here, because the first two mechanisms are extremely robust, and so this is, let's say, our core and the baseline of the attestation sub-mechanisms that we rely in Palantir. So having all these sub-mechanisms working together, at the end of the day, I stop here, we are able to detect and practically trigger a failure, an integrity failure, and spot a compromise, both in the underlying platform and in the core systemic libraries of Palantir, that is to say the microservices that constitute the Palantir service graph, and last but not least, the capabilities that are also measured, because it might be the case that we have trustworthy platform, trusted Palantir execution, so everything is intact, but a malicious developer uploads a specific or modifies a library and puts this in the catalog in order for an SME or someone to download this and practically, instead of protecting his or her environment, manipulating the execution and compromising the environment. So practically to work as a honest, curious, and malicious a malicious user. So with this sub-mechanism, we cover all these three, let's say, layers of cases that we can compromise. So I stop here. Sorry if I...
We have also prepared a demo for security capability attestation. So I will share my screen again. As Panagiotis previously said, security capability attestation monitors that the capabilities uploaded on the security capabilities catalog are not maliciously modified. So we will describe you the flow. A developer registers a new security capability into the catalog, and the Palantir administrator has to manually then verify that the capability is not malicious, and afterwards registers it into the attestation engine. Now the SME managers can onboard the capability, and the developer and the administrator can attest in order to verify that it has not been modified. In case the validation fails, the capability can no longer be onboarded, thus protecting the organizations using Palantir. For this scenario, we will modify an XNF file, so you will see that the attestation will fail. We're now registering a capability. And now the administrator will register the capability into the attestation engine. Now we are uploading a different XML file, replacing the file that the developer had previously uploaded. And as we expected, the attestation fails. That's all from us. Thank you for your attention. If you have any questions, they're welcome.
Or else we can continue.
So if there are no questions, should we move on to the second demo?
Yes, I think, Dimitri, we should. Yeah.
Antonio, would you share your screen?
If Daniel can share the screen, because later he will move on, we can start. So.
Hi, Antonio. Hi, all. I can share my screen right now. So, sorry. So, can you see my screen in?
Yes, perfectly.
Right now, no?
Yes.
In a full screen mode, no?
Yes, that's right.
Okay, thank you.
Okay, thank you, Daniel. So, hello, everyone. My name is Antonio Pastor from Telefónica. So I will make an initial introduction of this second demo. Later, we'll pass the floor to Daniel from the UPN just to progress on the detail of the demo. So this demo will focus on the crypto mining detection and also combining with a live intelligent threat sharing. So first of all, I will try to introduce the concept of what kind of threat we are detecting or using the PALANTIR platform. So if you can go to the next slide. Just to say that we have been focusing on the crypto mining problem. Basically, the idea is that in today's world that we have a wide use of cryptocurrencies, one of the main attacks that is happening around the malware today is the use of some kind of payload on the malware related with crypto mining or crypto jacking. That the idea is just to exploit the resources of the victims to make this mining activity. This is relevant indeed problem on the malware that has been highlighted in several reports for experts. Here is one reference about Kaspersky analysis that highlight the problem is really relevant. There are also other players, for example, Google. Recently, in his cloud service, has announced that he will invest more than $1 million focusing in detecting crypto mining on their cloud services. So this is a relevant problem, and indeed, when you detect crypto mining, it's not only the crypto mining, it's a malware that is happening that usually are related with other type of attacks on the environment that could be ransomware or denial of service attack, whatever. So being based on malware, usually one of the main propagation vector detector usually is this kind of piracy content or manipulation of software supply chains on, for example, based on manipulated libraries to include this malware, or containers and image and software that is running on servers and clients. So the main problem with this type of attack is that it's not clearly or is not easily identified. Why? Because his main focus is not to create a damage in sense of denial of the service of the services, or to make some kind of ransomware attack in order to obtain direct economical benefits from this kind of ransoms. Here, the idea is just to consume as much as possible the resources of the victims in terms of CPU and memory, and as a consequence, increasing the energy consumption and affecting to the hardware life cycle of the time that the hardware will be usable as a side effect of doing these mining activities. Other side effects usually is some kind of performance degradation, but sometimes this is not easily identified. So based on this type of attack, we have decided in the Palantir project to use this specific attack to leverage all the capacities, specifically focusing on analyze the network traffic and using the artificial intelligence for detecting this attack. If you go to the next slide. Here, basically, what we have done is to analyze the type of network communication that is happening on this type of attack that usually involve the victim software, sorry, and public mining pools that are usually available over public internet address or hidden behind some proxies or controlled devices by botnets owners. The good point is that being on network activity, it can be detected, and for that we have choose the NetFlow protocol that is supported on the Palantir framework for making this kind of detection. And what we have done is precisely improve the NetFlow information using some of the capabilities that Palantir offers that will be described later, and making this, enrich this NetFlow information with additional parameters like the packet per second and byte per second that are collected per flow in order to increase the machine learning capacities for detecting this type of attack. So doing this, we have deployed this machine learning model combined with a security capability around the NetFlow and make this attack. So we can detect it, make a remediation receipt, and also make a threat sharing. If you go to the next slide, here is the representation of the setup we have envisioned. So as you can see here, we have two different operators. In the lower one, the bottom one, we have the environment that we have deployed in Telefonica on the Phytonic lab. This is an open lab where we experiment different type of evolution on 5G network, and indeed we have cooperation with main players and research. And in this case, we have selected the 5G network connectivity provided by Ericsson. That means that we have used the radio on the core from a commercial vendor, in this case Ericsson, jointly with an edge server where we have deployed the Palantir framework in order to evaluate and make a validation of this type of attack. So we include some client that usually access through a customer router of 5G on accessing to the network, and this client has been infected with this crypto mining malware. And the Palantir Edge, the Palantir framework deployed in the edge is able to detect and mitigate locally this attack and generate a threat sharing information that in this case is delivered to the second operator that is represented here in Democritus, when there is another Palantir framework that collect the information and take the decision to apply equivalent remediation, in this case a preventive remediation, in order to block these mining pools for future type of attack for other compromised equipments. So now it's time to move to the demo. So I will pass the floor to my colleague Daniel, so he can explain more in detail this. Thank you.
Thanks, Antonio. So then we are going to validate how the Palantir ecosystem enables the detection of crypto mining activity within the network and how it enables the threat remediation to be communicated between the two Palantir platforms through the threat sharing functionality. So in this slide, we can see the high-level architecture for the demo. For this demo, there are two instances of the Palantir platform, one for the Telefonica side and another one for the Democritus side. And the demo consists of validating the threat sharing functionality between the both premises when a crypto mining attack is generated from the TID side. So to carry out the threat sharing between both Palantir platform, multi-tenancy support, functionality, and communication via virtual private network connection and Kafka cluster working as an intermediary data streaming service are used. So each environment corresponds to a particular tenant ID within the Palantir ecosystem, and this tenant ID allows sharing the same Kafka distributed cluster on both Palantir platforms for the intercommunication of different components within it and with a particular channel for each tenant. Then the threat sharing allows the Palantir platforms to share the recommendations and the remediation in case the threat happens on one of the two infrastructures. So as we can see in the Palantir platform is mainly composed by the data plane infrastructure for the deployment of the security as a service capability for monitoring and the remediation parts. These security capabilities work as network services following the NFV paradigm, responsible for the SME protection. For the particular case of the crypto mining traffic, there are two main security capabilities. One is the monitoring security capability for network flow monitoring, and the other one is the firewall security capability for the traffic filtering. The control plane infrastructure, this one, is composed by the threat intelligence system and the orchestration functionality. The security orchestrator is in charge of the overall lifecycle management of the security capability, and it's based on the open source Mano platform, which is aligned with the NFV paradigm. Well, the other component that conform the threat intelligence components of the Palantir complement the protection of the provided by the security capabilities with advanced analytics mechanisms based on machine learning and data engineering that provide automatically generate remediation to address the detected threats. And additionally, to demonstrate this particular case for the crypto mining attack, there are two additional systems: the client machine inside the Telefonica infrastructure hosting the crypto malware attack, and the crypto server reachable at internet, that is the attacker that received the result or the reward of the crypto mining challenge. So if we go to the next slide, we are going to go step by step explaining the demo. We will start from a base state where there are no security capabilities that are operational. For easy of explanation, we only represent one instance of the Palantir. So in such a case, the security capability developer of both Palantir platform needs to upload the security capability from the dashboard to the security capability catalog, and then the security capability is onboarded on the security orchestrator. We have a demo of this step, but due to lack of time, and we are going to ignore it because this is shown in the previous demo, and because the important thing is to showcase the cryptomagnetic detection and the remediation part, and also the threat sharing functionality, of course. So in the next step, the previously registered security capability is manually deployed from the dashboard. After that, the operator will be informed about the security capability deployment. So we have also another demo of this part, but we are going to ignore it as well, because the important thing is to demonstrate the cryptomagnetic attack and the threat sharing functionality. So once the security capabilities are deployed and operational, we can validate the detection and remediation functionality of the PALANTIR platform for the cryptomagnetic attack. And we will show a theoretical and practical demonstration now. So in the next step, the cryptomining malware is going to be triggered, and a client machine will simulate sending different traffic profiles to a server machine with both encrypted and not encrypted connection of cryptomining protocol, as well as also vending traffic. All the traffic will be monitored through network flows collected by a net flow collector. So in the next iteration step of the workflow, the threat intelligence activity comes into play. First, the semantic data aggregator, the SDA, normalize the net flow monitoring data according to a YAN model, aggregate unidirectional flows into bidirectional network flows, and also calculate additional features such as commented before by Antonio, packet per second and byte per second, useful for the analysis and for the detection of threats in the network. Mainly in such a case for the cryptomagnetic attacks. And after that, the distributed collection and data preprocessing component, the DCP, is in charge of collecting data coming from the SDA, running additional preprocessing tasks for enriching and structuring the data following a CSV schema, which is finally the input for the cryptomagnetic detection system, the CDS. So in the next step, the CDS is a machine learning model trained with classification model based on random forest classified for detecting cryptomagnetic traffic from net flow-based monitoring data. And this CDS detects the threat, marks the flow as a cryptomagnetic traffic, and the TCAN, the threat classification and management component, receive the marked flows and classify the threat as cryptomagnetic malware. Once this component, the TCAN, receive the detection of the threat from the CDS, it generates an attack report for the recommendation and the remediation component, the RR tool. This RR tool computes the remediation for the detected threat for the specific network scenario. In this particular case, it proposes a reconfiguration of the security capability, the IPT net flow security capability with the monitoring part and the firewall part, and perform it through the security orchestrator. Then the threat sharing happens to do proactive remediation into the remote environment. So in the PALANTIR platform, the security orchestrator of each PALANTIR infrastructure in both sides, in the Telefonica side and the Democrito side, reconfigures accordingly the IPT net flow security capability, accordingly by adding new rules which block the traffic from and to the malicious server. So in the following video, we are going to showcase the cryptomalware detection and remediation processes. In summary, a cryptomining malware is going to be triggered at the Telefonica premise, and it is going to be detected there and remediated at both sides, in the Telefonica side and in the Democrito side. So on the left hand in the terminal, we can see the simulation of the cryptomining malware. When the traffic generated, a threat flow with cryptomagnetic profile is going to be sent, and then the threat intelligence function comes into play. In the next terminal tab, after the data preprocessing performed by intermediate component of the threat intelligence system, we can see the output of the cryptomining detection system that provides prediction results about the cryptomining malware for each network flow that is received, and the CDS detects the threats, generating an output for each flow with a score about the malware prediction. So then the TCAN component will classify a threat as a cryptomania attack in case the prediction score is high, triggering a corresponding alarm to mitigate the threat. So once the CDS detects the threat, generating an output for each flow as this one with a score about the malware prediction. And for the attack report for the recommendation and the remediation component. Then the RR tool, the recommendation and remediation engine, compute a remediation for detected threat, reconfiguring the security capability through the service through the security orchestrator, adding new IP tables rules to block the traffic in local and remote side. In the local side, that is the Telefonica side, the remediation blocks the single connection between the infected machine and the attacker. And then in the remote side, the IP tables rules block the traffic for the Democrito side. So then the threat setting will happen to do the proactive remediation through Kafka broker. This is the following step. To do the proactive remediation in the remote environment too. And the proactive remediation block all traffic, that is the ongoing and the outgoing traffic to and from the attacker machine. So in the right hand, we can see the different rules configuration in the Telefonica side and at the top, and in the Democrito side at the bottom side, with the different rules that are configured to block the traffic to the attacker machine. So if we go to the next slide, finally, something that we have not included in the recorded video is that the security capability, the configuration request, and also the subsequent remediation of the threat are sent from the security orchestrator to the dashboard in order to notify to the users about the mitigation process, about the threat mitigation process. So this is all about the Demo 2 presentation for the Pilot 3 of this Palantir public event. Thank you all for your attention. I don't know if you have any comment or any suggestion or any question. Thank you all.
Thank you, Daniel. Okay, since we don't have any questions, we can proceed with the final demo. I will take the floor now. I'm using my colleague's mic because we are in the same office. We will proceed with the presentation. Okay, I assume you can see my screen. Okay, I guess we can. So we're going to present the kind of denial of service in 5G infrastructure. Okay, now the overview of this kind of denial of service attack is a SIM flood, where the attacker overwhelms the target system by sending a large number of SIM requests. This to a gateway in our case. So this has many effects regarding the system itself and its health, and also the quality of service that a 5G provider can provide. One big issue is the system resource exhaustion, like RAM and CPU, since the system is struggling to serve, to respond to those SIM requests. Another effect is the increased latency for the legitimate users. This has many effects. If we have real-time applications, you can imagine if we have a video streaming service or something like that.
the overall downgrading of the quality of the 5G services, the downlink and the uplink throughput. And also, if this scales up, if there are multiple attackers, this could lead to a complete denial of service where you can bring the whole system down. Regarding this attack, is quite accessible and easy to perform, since the SIM flat can be executed by many open source softwares. We are using for this demonstration the HPN3, the open source tool. And also imagine that we have a 5G operator where he serves his legitimate users. So the attacker can also have a mobile network to connect to this network and then use his mobile phone to execute this attack. So this is the flow of the attack. The components are involved. We have the legitimate users, we have the 5G system, the attacker, and the PALANTIR framework that is responsible to monitor and also notify the operator about this specific attack. Let's continue to the next slide, please. Also, I should add that we were going to show this schema live. I mean, we will showcase, we will demonstrate the actual equipment used for this demo. So our goal is to introduce the effects of the SIM flat attack, as we have mentioned in the previous slides. The attacker uses a 5G enabled phone to connect to, as any other user. He uses to tether the connection from his mobile to his actual PC, and this would also be done if he has a rooted phone, since Android phones and other mobile phone operator system distributors have some security policy regarding this. You can't install anything in your phone. So in any case, if the attacker has a rooted phone, he could actually perform the attack directly from his phone. We have chosen, since we don't have a rooted phone, we have chosen this setup is exactly the same. The attack is performed to the 5G system gateway, and the legitimate users experience the effect of the SIM flat attack. We will demonstrate the video for this to showcase specifically it's the downlink that's affected. And the second demonstration is the actual attack. By using the PALANTIR solution, the 5G system uses the Suricata enabled Azure security capability to monitor the traffic. The attack is detected, the operator is notified, and the operator performs the mitigation actions. In this demonstration, we have selected to add the human in the loop scenario where the operator is able to have the authority to proceed with the mitigation actions. So we will continue with the video where we show the effects of the attack. Okay, this is we are using here the iPerf to showcase the bandwidth and the quality of this normal. At some point, the attack will proceed. This is the attack, and we have to the left, to the right side, we have the ping to show that the attacker has connection to the actual 5G network. Okay, now the attacker proceeds with the attack. It's the ping, it floods the gateway with the SIM requests. This is from the left side. Now we can see that the downlink is actually 0. This is the effect of the attack.
For the other users?
Yes, the legitimate users experience a low bandwidth, a 0 bandwidth in our case. Okay, this is yes, this is the Wazoo that detects. Okay, that is not part of the actual infrastructure. It's from the previous execution we had. But here, if the operator has
Selected.
that the mitigation action should be automatically, it's also possible. Here, the attack is stopped automatically. So we will proceed with the actual demonstration where we use the PALANTIR framework. Before doing so, we would like to show you the actual infrastructure that is actually used for this demonstration.
Okay.
Here, I will do my best to narrate what we see. This is the 5G system. It's a Microsoft one that provides the 5G connectivity. If you go to the mobile phones, those are the legitimate users. And from the right side, okay, go to the attacker one. This is the attacker with the tethered. Okay, this is the attacker with a tethered phone that he also has a connectivity just like a normal user. So let's continue with the demonstration. Okay. Okay. So this is exactly the same setup that we have shown earlier.
First of all, let's say that we selected to present in a video because there are multiple screens that we need to share, and it's not easy by using the teleconference mode.
Yes, so this is an actual footage that we have recorded yesterday. So we have here the mobile phones. This is the mobile phone tethered to the attacker, where the HPing is executed. Here we see the notification through the PALANTIR dashboard. It also contains the malicious IP, which should be blocked, must be blocked. So it's now the operator. Okay, now we showcase that the attacker continues to have connection to the 5G infrastructure. Here, the operator enforces a policy where he stops the attack. And this is it. Let's continue with the presentation. Go to the last slide. Yes, okay, this is the questionnaire we have mentioned earlier. Please, if you have any questions, I'm happy to answer. Thank you very much. Okay. Since there are not questions, maybe we should close the demonstration here. Okay. Thank you very much for your participation. Hope you have a great summer. Thank you all.
Thank you.
Thank you. Bye-bye.
Thank you.